contrary, I'm a bit ahead of time and I am preparing this week already in this week, which is actually what it should be normally. And this week we are jumping back to the beginning. So you can remember in the very beginning we were talking about how to deal with plane. And we thought that in the plane we want to have something like the notion of points and also the notion of vectors which bring us from one point to another point. So the vectors are independent objects and the vectors are considered as change of position while the points are the positions themselves, right? And that's exactly what we have to deal with anywhere as you work with data. So you are interested in the values and in the fact how the values change. And this is the change of position. And this was R2, but who cares about the dimension? So this could be the same for the dimension being 10,000 or 10 millions or whatever, right? So this is the basic concept of affine geometry. And if we look at it here, so this is what we shall be doing, right? So we have the affine spaces, the affine maps will come next, and the objects which are linked to that. So it's something very similar to vector spaces, except only the changes are the vectors, and we can add the changes, right? So if I add another change here, then of course I get the composition of those two, how to get from the first position into the third position in a straight way, right? So this is what we want to keep track on. And of course the easiest thing, the most simple thing is the standard affine space, which happens if we identify the space, the R2, with n tuples of real numbers, right? And as soon as we do that, then it seems like there is no difference between the positions and the changes of the position, because they are both n tuples of numbers. But it's wise to keep track and know that it's different, and that's formalized here. So I will change the color. I don't yes, here I don't like the orange one in marking, so we call it the standard affine space, and this is just the Rn, which we view in two different ways. First is the Rn of the position, so I will use the position notation as the capital letters, and the vectors will be small letters. And what we do have is the addition. The addition is simply adding the values. Yes, so to the position I'm adding the vector, and this is clearly these three properties. So the first property is that there is the only option how not to change your position, and that's by adding the zero vector. And then it has to be associative with respect to the adding of vectors, so it doesn't matter whether I first add the vectors. Notice this is a different plus than this, although it looks like the same one, but it has different meaning. Here I add the vectors, whereas the adding of the result is something, right? And I can do it twice this way. And for every 2 points there is exactly one vector which is just bringing the first one into the second one. So this is denoted as the subtraction of the point A from the point B, which is exactly what's happening in the coordinates. So this is how we formalize the thing, and it looks like we don't need it at all because we didn't put anything new there. But then there is this real definition of an affine space, not the standard one, but the general one. And here we simply make the difference between the points and the vectors. And this plus is a new operation which has to exist, right? And in the tutorials in the left-hand column, in the practical approach, you will see a couple of examples which don't look at the first glance as the standard space, because the P and V will be completely different objects. And this is something which we shall be meeting again and again in analysis and in other parts of mathematics in the future. So we have just the operation adding points and vectors, and we request that the three obvious things from the standard vector space hold true for the abstract ones. So in particular, for each vector we have got the translation, which shifts the points by adding the constant vector v, right? So that's it. Right, now what is the dimension of the affine space? So this is the dimension of the difference space. The space of the vectors is called quite often in the literature difference space. Somewhere you would meet the name modeling space. So we say that the affine space is modeled over some vector space. And of course, as always, if we just deal with the abstract situation, the things which seem to be obvious from the standard one example have to be proved. So we simply have to prove all these things, right? But they are obviously following from the axioms. Just give it a thought and you will see. And now we are coming to the identification of the affine spaces with the standard affine spaces. This is what we did with the vector spaces. Here it will be roughly the same. So we simply have to fix one of the points, like fixing here, say this one to be called 0, right? So if I just fix this one and call it 0, that will be the origin. Then of course, by the axioms, adding a vector brings me exactly to one point from the origin, and it's uniquely given by the point, I mean the vector. So it's identification of the affine space with the modeling vector space. And if I, on top of choosing the origin, so say this would be O, if I choose also a basis in the vector space, then I get a unique expression for every point in my space. It will be the A0 plus linear combination of the vector space basis. And we talk about affine coordinate system. And the n+1 tuple, the origin A0 and the basis of the vector space is also called affine repair or affine frame. Right, so we shall use this notation which goes back to the vector spaces. Remember, I underlined the letter to indicate that it's a basis. Right, so this is quite straightforward. What does it mean to have a subspace? So the subspace is a little bit more subtle here. So of course we need to have subsets which would inherit the structure and will become affine spaces by themselves, right? So this can be obviously done in two steps. So first we can take all the differences between points in my subset Q, and we insist that this W would be a vector subspace. And then we insist that adding the vector from the vector subspace, which we already realized, to any of the points in my subset must be again in the subset. So it seems like superfluous, right? But if you just give it a thought, even in dimension 1, imagine I would just take away one point here, right? So I would leave all the R and remove one point. Then of course the set of all the differences will be again R, but it's not true that if I take a point here I could add any vector, because if I add the vector, say from the point B which I removed, so the difference of B minus A, then simply this is not fulfilled. So simply I don't want to see these kind of things as subspaces, because they are not affine spaces by themselves, and therefore the second condition is strictly necessary. Of course, what we can do is we can take any set of points, which we shall call generators of an affine subspace. We can take all the differences between the points in M. We take the linear span of them, and that's what we call the difference space of the subspace generated by M, because then we can very easily very easily define the subspace by taking one of the points of the M and add all the vectors from this computed difference space. And this coincides with the more usual abstract definition, which is here. So the affine hull could be also defined as the intersection of all affine subspaces which contain the set of generators, right? And as it's written here, if I fix one of the points in M, the affine hull will be exactly what we told now. And of course, if we take a basis of this computed difference space, then we can write the subspace Q as in a form which is called a parametric description. And it's just like we saw the general coordinates. Now we shall have any of the points there could be taken as an origin of the subspace, and we simply add the linear combinations, right? So that's very straightforward and easygoing. And here is an example, right? So if you take any affine coordinate systems of an n-dimensional affine space A, so it's an abstract space, so then the k-dimensional subspaces are exactly the sets of solutions of systems of linear equations, and the linear equations must be solvable, because we don't take an empty space as affine subspace. So the affine subspaces are always non-empty, because the smallest affine space, the zero-dimensional affine space, is just one point, right? Just one point, not empty. It's like with the vector spaces. The smallest vector space has got the vector 0, nothing else. So here is the same. So we have to restrict ourselves to solvable systems of linear equations, and of course, if it's on n-dimensional space, then it must be linearly independent equations in n variables. So you see, the formal approach to the affine geometry, defining the affine spaces in the general way, means that we have formalized the concept of the solutions of linear equations, systems of linear equations, because here we get it, all of them are exactly affine subspaces, and that corresponds to the fact that you always can find a solution, all the solutions, by taking one particular solution of the given system with the non-zero right hand side in general, and this will be one point in our solution space, and then you add the solution of the homogenized system, so with 0 on the right hand side, and that's exactly the modeling or difference space for the space of the solution. And again, we can come back to what I was telling in the very beginning. If you have a set of, I don't know, 10,000 equations, but there are only 3 independent ones there, well, no, wrong. If you have 10,000 equations and there will be only 9,993 independent ones, then the space of the solution will be 7-dimensional affine space. independent of the fact that you have got so many coordinates, 10,000, right? So that's again something very important to have in your mind if you handle big data. So very often you are handling big data, but you are interested in small dimensional gadgets there, which will be of the kind of an affine space. Right, so the proof here is straightforward. It's not difficult. The important step on the way is to understand how the coordinates are changing. So what does it mean, a coordinate transformation? And here it's clear. So if we compare what's happening to what we know about the vector spaces, so here we not only change the base in the difference space, in the space of the changes of positions, but we also change the origin. And that's exactly what we were drawing, if you remember, in the third week, or which one it was, in our beginning of the semester in the plane. Just go back there and seeing what's happening there in the most simple situation, and it's exactly the same idea, the same thing. The dimension doesn't play any role here, right? So you see that the coordinates in the system in the frame with B0 and V will be written this way, so let's call them new coordinates, so the dashed ones. And of course I can write it this way, right? So it will be, I start in the point B and I add the vector which moves me to A0, and then I have to express the same thing here. And so clearly the new coordinates will be computed in such a way where the matrix M is just the matrix which expresses the basis U in terms of the basis V, right? Because for each of the V's we express them via U's, and that's exactly what we have to write there. And in the matrix notation you get something very familiar, this, right? So no surprise. So we simply have the same way of transforming the coordinates by multiplying with an invertible matrix, which is n times n sized, and we have to add the shift of the origin. That's it, nothing more. So this is very simple. And of course, if you then look at the examples, so how to see the subspaces, then it's very easy. So if you have one-dimensional affine space like here, then the only subspaces are points, so it's zero-dimensional subspaces. In two-dimensional, it's a plane. The subspaces are the points or lines, so because lines are the affine subspaces, it's obvious. And of course, as we saw, the affine subspaces can be either written in the parametric way, or they can be expressed as a solution of system of equations, and that's the unparametric description. And in three-dimensional space you would simply have points, lines and planes, and this goes on, right? And you can just restrict your mind to think in the dimensions you can imagine, and be sure just doing the operations then which holds true and work for all the dimensions, and that's exactly how the mathematician would work. Well, and last thing for this presentation is a new operation, right? So in the case of vector spaces, the absolutely crucial concept is the linear combination of some vectors, right? So we take finite number of vectors, we multiply each one of them with a scalar, and we call it a linear combination. We get a new vector, right? And the linear independence was based on this. What can we do with the affine space points? So we have k plus 1 points, and then their affine hull is definitely possibly written this way, right? So this is the affine subspace generated by the k plus 1 points. And of course, if we choose coordinates, then, well, that's it's a bit unlucky that the typing was not so it's not typeset correctly. So what you get is you get some t0 times the origin, right? Because you see the t0 will be, the origin will be 1 times here. So the t0 will be 1 minus t1 minus t2 and so on minus tk. That's the t0. And then we add this a1 plus and so on tkak, right? So this is what you get for every point in the affine hull of the k+1 points. And just taking account what I wrote here, if you sum up all the t's, then of course those with positive indices will cancel each other. So you clearly get this. So an affine combination of points is a combination which is written in such a way that formally we write something like a linear combination, but of points, not of vectors. And the sum of the coefficients must be 1. That's the big difference to linear combinations of vectors. Affine combinations have the sum to be 1, right? And that's what this definition says. And of course, then in every coordinate, as we already saw, it will be just the linear combination of the coordinate expression of all the points, but with the condition that the sum is 1. So you can imagine it in low dimension, right? So say we are in the plane and I have got, say, 2 points only, and now I take the linear combination. So the origin will be somewhere here. So that's the origin all, right? So I've got 2 vectors here, and I take their linear combination, right? So I definitely could get all the plane by taking all the linear combinations. But if I restrict the sum of the coefficient to be 1, it draws exactly the line we expect, right? So if one of them was 0, then the other one must be 1. That's the 2 points. And all the others are just affine combinations. The affine combinations are absolutely crucial thing when handling data, because you usually decide on some qualitative or quantitative parameters or behavior or whatever by computing some means. And computing weighting means exactly to do some affine combinations of your data. So then computing means it means just defining the right structure of the affine space is then governed by guessing the right properties, for example stochastical properties of your data sets. And then you have to choose the right structure and to compute the means, right? So just have this in mind, and you will come back to that. Affine combinations are extremely important concept. Right. So I think it's time to stop. So I will continue in a minute.